Hi, we're here today to review the geometric concepts within BC Calc. So in particular, this was in a unit that we call geometry. And as a subset of that unit, we did all things related to polar graphs. I'm going to start this video with looking at the examples that are about polar. So that is, I believe, problems 1 and 2 and 4. And then after that, we'll move into the ones that do not involve polar. So if you're looking just for that part, you can kind of fast forward because that's going to be at the later part of it. Okay, so I made a note at the top here of my screen that number 1 is a lot. This question is not from an old AP test. It is from a different author, and basically made a question here that was like a lot of things. Okay, it was quite a lot. So just don't panic too much. I don't think the polar is excessively tested. Nothing is excessively tested, except for maybe fundamental theorem. But this question does involve quite a bit. Okay, so this question asks us to find the equation of a tangent line. And anytime we want to find the equation of a tangent line, we should think we need a point, we need a slope. Okay, so do we have either of those? We have sort of those, not exactly at all. This is an angle value, and that angle value could give me a point because I would plug in this theta value here and here. I would plug in the particular r here and here, and that would give me an ordered pair. So that's what I would go ahead and do, right, is to find that value of x, that value of y, and then that turns out to be 0, negative 6 pi. Okay, so this is from doing x equals 4 theta, right, times cosine of theta. And y equals 4 theta sine of theta. Okay, so that's going to be my ordered pair. To find the slope, we should know, and by the way, I should say this also, this is something we need to know. That's just a fact, okay, x and y. This is also a fact, right? The slope in polar is a lot like the slope in parametric, right, where you take each individual component, dy, d theta, dx, d theta, divide, and that gives you your slope equation. So here, I'm going to scroll down. I tried to make this video shorter by having some of the writing done ahead. So down here in blue, you can see that I wrote out the derivative of y with respect to theta, the derivative of x with respect to theta. That comes from looking back at these, right, and knowing that r is 4 theta in this case, okay? So find the derivative of y requires product rule. Find the derivative of x with respect to theta requires product rule. And then you substitute in your theta value, and that gave me this slope. So I have this slope and this point, and if you put those together and maneuver a bit, you will see that that is answer choice C. Now that question took me over 5 minutes to work fully. So understand that that question is a lot. That is definitely at the high end of expectation level in terms of just amount of detail without a calculator, okay? This next one is calculator active. The only reason that we would ever switch to a polar format on our graphing calculator would be to see a picture like this and to be able to understand the direction in which this is graphed. So I already have an arrow here where this graph begins and it loops around like this. It comes to the pole. Remember that at the pole, the r value would be 0. And then you come looping through this, oops, sorry, bad drawing. Then you come looping through this inner loop, come back to the pole again, and then you come around this way. Okay, so that is the orientation of the graph, just to help yourself understand what you're looking at. Other than that, you really don't need to be, other than that, and using the calculator tools, like in the calc menu, there are some things in polar that you might choose to utilize. But other than those two things, I can't think of a reason to have to be in polar mode to do a polar equation. In fact, a lot of times we don't want to be in polar form to do a polar equation. It's important that you know to find area in the polar life. It is the integral of 1/2 r squared d theta. The bounds here would be theta values because that's what this is telling me, okay? So it asks me to figure out the area between the two loops. And my understanding of that would be then I want this region here, okay? And remember that as we're thinking about polar area, we're thinking about wedges. So we have wedges that are coming out from the pole. So when I get to this pole, when I get to the pole in making my graph, remember the direction of the graph. This would be the wedges that would come out. But then after I exit that loop, there's going to be wedges that come out that are like this. And notice how those wedges overlap the wedges that we already shaded in. And so we don't want those both to be counted, right? The overlap is a problem. So we need to think carefully about how to construct our integral, okay? So I would like to know when we are at the pole, okay? I'm now going to, I think, utilize my writing down here. So we are at the pole. We are at the pole when r equals 0. So if I set my equation equal to 0, I get these two angles. So those are the theta values that take me right to the point that I am just highlighting here as yellow, okay? Now, if you think about the inner loop, okay, the inner loop is the part that I've shaded in purple, and that is this part of my work, okay? My inner loop is going to be just between those bounds we just found, and then do my area, okay? Now the whole shebang, right? Remember that we shaded, my shading up here is messier, but more accurate in some sense. All that red part is coming out from the pole, but it's also including that inner loop, okay? So I would like to do that whole part, so coming out of the inner loop, like right through here, okay? That's going to be starting from 5 pi over 6 and going all the way back around to here, okay? And that would be at 13 pi over 6. And then I'm going to find that area, and I'm going to subtract those two values. Now, the answer choices are slippery. They're very close together. This is the correct answer. This was adding, I think, instead of subtracting. Like all these that start with 30 are really easy to get if you just make a small mistake. So just bear that in mind as you are setting this up, to be cautious about attention to detail, okay? We're going to skip over number 3 right now because I told you I'd do all the polar ones first, or talk about the polar ones first. And number 4 is a much nicer question in that one, even though it has 2 polar graphs instead of just one of them is a circle. And so you would have the option of thinking about the circle part as a circle, or you could think about the circle part as a polar graph, because it is, okay? So for instance, if I wanted to think about this section in here, okay, that is a section that on the circle would have bounds 0 and pi over 6. And the circle equation was with a radius of 2.5, so r equals 2.5, or 5 halves, if you want to write it that way. Squared 1/2 r squared d theta is my area, and then I could utilize symmetry and just say, well, there's 2 of those, 2 sections that are that big, okay? And then the next section of region R is this section here, but notice that that's not going out to the circle, that's going to the other equation, the one that has like a little dent in it. So that's this equation. So I'm going to have 1/2 r squared d theta for that. And I do need to figure out where these, I was going to say we need to figure out where they intersect. No, they told me where they intersect. Great. So I can just use that. Now, if I did need to figure out where those 2 equations intersect, I would not do that in polar. I would say, here's one equation, the circle, here's the one with the dent, and I would put those both in my y equals. Y equals 4 minus 3 sine x, y equals 5 halves, and I would look for where they cross and make sure I'm in radian mode, because this is freaking calculus, you guys. We're always in radian mode. Okay, so that's the yellow section. And then the purple section I could do as a polar thing as well, but I could just say, well, that's half of the circle. So wouldn't that just be 1/2 pi r squared? I'm just saying, okay? Now, I could have done the red sections as part of that as well, right? Just knowing that this was a 30-degree section and this was a 30-degree section, I could figure out that I had, 2/3 of the circle, whatever. But, whatever works is fine, okay? So work that out, yay, okay? Then part B is really weird. I've seen this in at least one old FRQ. I think that's what the author of this was modeling it on. Basically what they're doing here is they're trying to tell you to let theta and time be like the same thing, sort of, right? So for every 1 radian, there's 1 unit of time that passes by, right? So if you imagine your polar graph ticking out as theta passes, it's like you have a clock that's based on theta, if that makes sense, right? Like minutes equal angles. Yeah. Anyway, basically what they're doing is allowing themselves to have a stem of a question that's polar, and now they're kind of making it into a parametric situation, right? So they're saying, let's think about things relative to time, but time and theta work the same, okay? So now they want us to find the value of dr dt. Well, dr dt is going to be like finding dr d theta. And so that should be easy because we have an equation that relates r and theta, so it's just taking a derivative. And then they want you to evaluate that derivative at pi over 4 and then say what it means. Okay, I'm going to use previous writing just to speed things along. Okay, so right here, so dr dt is like dr d theta. This is the derivative of that. Okay, then evaluate that at pi over 4. Notice my notation. I do think it helps to like signify that you are evaluating at a specific value. I got something negative. Now, it asked about the motion, the motion relative to the origin. That's another way of saying relative to the pole. So we know that this is one of those times that we have to think about 2 different signs. We have to think about a sign of a derivative as well as the sign of r. Okay, we have to think about dr d theta or dr dt, whatever. That rate of change sign, also the sign of r itself. Because remember how in polar you can have weird things happen when r is negative. It's like you walk backwards. So 2 signs, much like when we talk about if the particle speeding up or slowing down, right? We have to look at the signs of velocity and acceleration, right? The Prius principle. Same idea here, we have to be looking at 2 different signs. So I know from right here that my dr dt is negative. And then if I just plug in pi over 4 to this, I find out that that gives me a positive. So since I have a positive r, but the rate of change is negative, I know that we're moving toward the pole, okay? Yeah. If you need more on that in the geometry packet, there's a little chart of the 4 cases. I would encourage you just to think though, right? Think about the fact that if you are plotting a positive r, you're going out, and then a shrinking in that would bring you closer to the pole. Right? A shrinking in this r value would bring you closer to the pole. All right, this next one, you are asked to think about right-left motion, right? I know that because it's asking about dx dt, and that's right-left motion. I know that x is r cosine theta, so here is my statement of x. This would be my derivative of x using product rule. And then I didn't show you all the nitty-gritty here, but you just plug in pi over 6 for all of those angles, and it's a bunch of unit circle hoo-ha, little simplifying. But the point is that you get a negative number, okay? So you do enough that you know the sign, S-I-G-N kind of sign, and once you know you have negative, that means that if dx dt is negative, my particle must be moving left. Now, it might not be moving straight to the left, but like if you have something moving on a diagonal or moving on a curve, right? In terms of that horizontal component, is it going more to the right or more to the left? Okay, that is what is being asked there. Okay, we got through the polar part, you guys. That's great. Okay, the rest going to seem not so bad, in my opinion. Okay, I think the polar is kind of a slippery slope. Okay, all right, so number 3. I'm going to use my written out work, apparently, because that's what I scrolled to. And in this problem, this should be very straightforward question. They tell you the areas of regions A, B, and C are those numbers respectively. I have drawn those in my picture. Bear in mind that if I were then to integrate, this 5 would be negative, this 1 would be negative if my bounds are left and right set up properly, okay? Now they asked me to consider this statement and figure out what that would equal. Well, you can see my work down below. So I split this up. This is not the only way to do this, but I chose to split it up into this integral and this integral separately. The first integral, I just took as the 3 different regions with signs assigned accordingly, because -4 is less than 1, so everything is going to work, so positive is above the axis, negative is below the axis. And then for this last part, I just thought about this graphically and said, well, if I had the function y equals 2, here are my axes, here's 2 units above, okay, y equals 2, because that's my integrand, and then I was going from -4 to +1, that would give me a rectangle with width 5 and height 2. And so that would give me an area under the curve that is equivalent to 10. All right, now that is not the only way to do it. You could also think about anti-differentiating this and getting 2x with the bounds 1 and -4. That also would give you 10. Okay, that's more than fine. Great way to think about it. Okay, so that was number 3. We need to talk about number 5. I'm lost in my notes right now. Can you tell? Oh, here. Oh, I did have notes by this. Okay, I forgot. Okay, so this one, hopefully seeing length of a curve makes you think arc length, but understand arc length is a tricky concept to get tested on because they often don't use the words arc length, right? They might say something about perimeter or something like distance along the path or something like that. I don't know. They try to hide it. Okay, but this is definitely an arc length question. Underneath, I wrote the 3 different formats that you might see arc length in, depending on what your variable is. If your variable is x, then these bounds would be x bounds, and the slot for the derivative would be a dy dx statement. If this is a dy, these would be y bounds, and this is going to be a dx dy statement. If this is dt, then your bounds would be time, and you'd have 2 different derivatives, each with respect to that parameter. Hopefully you can see that these all are very similar in structure. They're all based on Pythagorean theorem, honestly. So they all have that adding, and then squares, and then a square root, right? They're all based on Pythagorean theorem. Okay, so it says if the length of the curve from x equals 2 to x equals 8. Okay, now this is a huge help because they said these bounds are x's, and they are showing me here dx. So I'm using this one. Okay, that's the lineup. And now if I look at that, everything is matching up great. And so my dy dx squared has to be something that you square, and you get 81x to the 4th. So I'm going to go down here to my writing and say that means that dy dx has to be 9x squared. Okay, that has to be. It could possibly have a negative in there because the negative squared would be a positive 81 as well. And then I just looked through my answer choices. Which of these has a dy dx that's equal to 9x squared? And there's only the one. Okay, yay. Okay, is that true? There's only the one? Ooh, maybe there's not only the one. Maybe I just didn't think hard enough about this. This one would have a derivative of negative 9x squared. This one would have a derivative of negative 9x squared. Oh, and it has to go through that point. That's the other thing. And the curve has to go through this point. So you can deduce it from those 2 facts together. Okay? All right. I think we're moving right along to number 6. Oh, number 6. Glory be. This is just classic geometry type question on a calculus exam. Okay, so notice here they are letting us use our calculator. So we don't have to do the heavy lifting. We just have to do the setting up of integrals and understanding our shape. So I know that the cube root of x is like x to the 3rd, but on its side. So it's like this. And I didn't draw that great, but kind of just go with me. And then 1/4 x is going to be a line. Something like that, okay? And we're just looking at the first quadrant, so we just need to focus our attention up in this region, okay? Or you can just graph that on your calculator, no problem. These are going to cross, let's see, do a little mental math here. They're going to cross at 8, 2. as well as at 0, 0. Okay, so here's region R, this part right in here. And to find the area, we want to do top minus bottom in this case, because we can set this up relative to x very easily. So my top function minus my bottom function, like that. If I want to revolve around the x-axis, I'm going to be going this way. That's going to give me a washer setup. The purple will be my big radius, and the green on my graph would be my small radius. So big pi r squared minus little pi r squared. Something like that, okay? We'll get the numbers as answers in just a second. Okay, if we're revolving around the y-axis, then going out to green would be further than going out to purple. So green would be my big radius, and I would need to reorganize for the opposite variable on each of these equations. So I would have my big radius be the green, so that's the line. And my little radius would be the purple, so that's this part. Big pi r squared minus little pi r squared. And then my bounds would have to be y bounds. And then the last part is a projected solid. So we want perpendicular to the x-axis. So these blue lines that I'm drawing are the edges of the squares that are going to pop straight out at us. So the length of a side in this case would be the cube root function minus the linear function. And so area of a square is side squared. So I'm going to take the side and square that total. If this were some other cross section, I would have, like, if it was semicircles, 1/2 pi radius squared, I'd put in whatever expression I needed for the radius, or whatever the case may be, right? Whatever other shape you might have. And then this would be 0 and 8 because we're doing in terms of x. Okay, let me scroll down to get the decimals for this for you to check your calculator work. Okay, so all my calculator answers are highlighted there in yellow for you. Okay, now the only variation that's covered in question 7 has to do with using other lines. So here to do the, in the last question, to do the area of R, you're going to be thinking about this distance. Okay, so top minus bottom. The top here would be the curvy function, and the bottom would be the line 1. I'm using an excessive amount of parentheses to try to explain my thinking on it. Okay, so it would be like that. Here, something that is a little tricky is they started talking about the horizontal line at -1, which is a little off the graph that was given. Okay, so let's just put that down here. And so if we want the volume that is generated when R is revolved around the pink line, then we're going to have a big radius here from curve to line, and our small radius is here from line to line. Okay, so that's going to be a length of 2. So the big radius would be 3 minus root x minus -1. I'm going to write it that way. I know you can write +1 as well. Okay, so that's my big radius. And then my little radius is 1 to -1, or in other words, 2. Okay, and so that would be my setup for this bit. And then the last part is asking us to look at cross sections perpendicular to the y-axis. Perpendicular to y-axis, have to go to the other variable. And we're looking at projections, okay? And so it's a rectangle, and the rectangles have a certain height. The height would be this yellow line, okay? And that would be one dimension of the rectangle. And then instead of projecting out to the same dimension, like being a square, it's going to be half of that length, okay? So if you take this equation, I'm actually going to scroll down. If you take that equation and you isolate the other variable, okay, you're going to get x equals the quantity 3 minus y squared. So this is one dimension of the rectangle. The other dimension of the rectangles is half of that. And then, hesitated too long, half of that. And then why do you think we have 1 and 3 as the bounds? You genius, of course, because this is dy, so we need y bounds. Okay, so that's the whole shebang here. The answer for part A was 8/3. You can work that out by hand because it is not that bad, which is why this wasn't calculator active. And then the reason that parts B and C just say write, don't evaluate, is because they are recognizing you don't have a calculator, and we don't really care if you can do all that by hand. Okay, I hope this helped, and keep up the good work, and you're going to do great. I'm proud of you. Thanks.